Hello and welcome to GOTO Unscripted. This time it's me, James Lewis, being the interviewer. I'm joined today by two people who are talking tomorrow in GOTO Aarhus about high-performance compute and quantum computing. So Stig and Soren, would it be possible for you to introduce yourselves to our audience?
Yeah, sure. My name is Stig and I'm a PhD in quantum computers and currently working a lot with quantum computers trying to make them do some interesting stuff.
Yes, my name is Søren. I have a PhD in quantum physics as well. I have been working with professional software development for 10 years about, and I'm now working as a software architect at Kvantify and try to bring quantum computers to real customers.
So welcome. Good morning, good afternoon, good evening, whatever time zone you're in. And I guess we'll get straight on with it. So I worked for a company called Thoughtworks many years ago, well, 5 years ago, 2018. We had Q# featured on our thing called The Radar. It's a publication. We publish every 6 months, Q#, but we haven't had anything about quantum computing since. It was sort of a super exciting thing that we were really excited about, starting to sort of, I guess, take off back then. So would you mind just going back to like 2018 and was that around that sort of time and talking a bit about where we are now with quantum computing?
Yeah, sure. So 2018 was about the time I started my PhD in quantum computing. And back then it was just some sort of fluffy area where it was fun because quantum computing is fun. But it wasn't anything serious. But then doing my PhD, hardware providers started to actually make these quantum computers bigger and bigger. And suddenly they became big enough to actually do something on it, to calculate small molecules. And that was never seen before. And then suddenly small companies started to pop up actually doing quantum computing stuff, and in the last couple of years now you can access quantum computers doing using cloud software.
And what sort of problems, I mean, you'll be talking about this tomorrow, what sort of problems are you talking about solving?
Yeah, so the biggest problem for quantum computing is probably chemistry, and that is drug design, drug discovery, and the making of batteries, because chemistry is inherently quantum mechanical. So it fits perfectly in a quantum computer. But other topic could be finance, which is also quite suitable for quantum computers, or logistics.
Okay, right. So these are all things that you're actively involved in looking at the moment, is it? Yeah.
Yeah.
Yeah. So we see some applications are more likely to be possible in the near term. For example, chemistry. Applications within finance is probably a bit further off, but we do have activities in all these areas where we just employ more traditional high-performance computing techniques.
And so what does that mean? So high-performance computing, the cloud, quantum computers, like unpack this for me, because I'm kind of intrigued as to how this works. Do you have your own quantum computer and then you like plug it into the cloud somehow? I mean, I don't know, how does all this work?
No, so we're a software company, so we don't do any hardware. We just access everything through the cloud. And the quantum computers are also part of the cloud, and they probably will be for many, many years. And then we just access the hardware through the cloud. Right now we're using the classical hardware, the normal high-performance computing. And then once the quantum computers are ready, we know how to use them because we're also doing that. And then we're ready to plug that in once they become good enough.
So you're kind of simulating quantum computers, not simulating them, but you're using, when you say HPC, do you mean like big graphics cards and this kind of thing? What's the...
Whatever compute resource is most reasonable. So there are a couple of different ways to assess risk in finance, for example, different ways to optimize your exposure to risk. And you can use quantum computers to solve some of these risk models, but you can also just maybe spin up 1,000 computers and do heavy calculations for a short while and get a result. So use either graphics cards or just a lot of CPUs, depending on the algorithms you want to run. One or the other might be more beneficial. And it actually very much in line with, well, right now maybe a problem is beneficial to run on the CPU, and in some years it might be good to do on a quantum computer, or maybe a new algorithm pops up and we need to do it on a GPU. We are agnostic towards that, and the products we deliver are going to be agnostics toward that.
Right, and it's a product company you work for. It's not bespoke solutions you're building, or?
It is bespoke solution usually, yeah.
So it's not a generic, hey, I can solve all your chemistry
problems.
No,
not at all.
No, but we want to be able to be able to solve a range of chemistry problems at some point and sell it as a generic solution, right? Not for a specific company.
Oh, super cool. So, I mean, I know a little bit about HPC, not a huge amount, I have to admit. I know a little bit about quantum mechanics, not a huge amount, I have to admit. Full disclaimer, I have a very old undergraduate physics degree, so that was going way back. And I didn't do well in advanced quantum mechanics. I will have to admit that. But I know some little bits in here and there, you know. So for things like HPC, I mean, typically you've got a number of different types of problem, like some which will be optimized for, as you say, like CPU, or some that are going to be massively parallelizable that you can run on big arrays of graphics cards. How do they sort of then translate into the world of quantum computing? How would you, I mean, is quantum computing suited to one type of calculation or another?
You can't just take your problem on a classical computer and put it on a quantum computer. That's very difficult. It's not all problems that are suitable for a quantum computer, so you have to create some software that does it in a quantum mechanical way, and that's not easy. That's why you need companies like us to help you do that. But again, it's not all problems that are inherently useful for a quantum computer. So that's why we mentioned quantum chemistry, which is the thing that most people think will be the first application of quantum computers.
And I've read a lot recently about, for example, machine learning being able, like deep fold. If you come across deep fold, and then like machine learning has solved protein folding apparently now. It's a pretty exciting thing. Yeah. Is it those sorts of problems that you're looking to address that?
Not usually, because machine learning problems usually have a lot of input of data. And quantum computers are not very good at handling data because data is usually classical. That is something we know from the classical world. And that's not quantum mechanical. So therefore we need something that is quantum mechanical and not just a lot of data. And molecules are quantum mechanicals. So therefore it is not, data-driven problems are not suitable for quantum computers. You need something which is more, it's suited in a different way, that you need this molecule structure that you can plug into the quantum computer.
I remember looking at Q-Sharp a little while ago, back in 2018, because I thought that was kind of interesting. And I sort of, with my classically trained programmer's brain, went, oh, okay, that's kind of it. So how does the programming paradigm change between what I would consider, kind of classical programming, for HPC or whatever, versus what you're having to do with quantum computers? Is there a complete shift of mind?
You've been programming more on the quantum computer, but there are some really radical differences. For example, all calculations has to be reversible, which means that if you do something, you should be able to undo it. So you cannot just multiply two numbers, because if one of them is 0, you lose information. So there's a lot of constraints. You cannot copy information. You're used to be able to make a .clone or whatever. You cannot do that on a quantum computer. It's physically impossible to do. So there's a lot of practical, it's just a completely different way of
And right now, quantum computers are very small. So you have like 50 bits or quantum bits. And that means that you're doing a basic operation, like a NOT operation. So that's what I'm coding is basic operations at the moment.
So when you say basic, you don't mean like as in basic the language. You mean
the
basic like almost assembler, essentially writing in logic.
It's even more low level than assemblers, right? Because you're addressing individual physical bits with individual logic operations. You don't have virtual memory. You don't have a stack. There's almost nothing, no abstraction.
Wow.
But all of that is probably, hopefully, something that will come in the coming 5 to 10 years. But right now, it's very basic.
But that's also because we don't know what the good abstractions are going to be yet, right?
So can you foresee a time when, myself with a sort of tinkerer's interest in this kind of thing will be able to maybe write a classical program and it would be like transpiled into code that can run on a quantum computer, like that kind of thing? Or is that way off in the future? We don't even know if that's possible to do yet, kind of thing.
I think at some point, but right now you have to have a problem that's very suited for a quantum computer.
Okay.
And that is probably the way it's going to be the next couple of years. So unless you're doing chemistry or something else which is very suited for a quantum computer, you're probably not going to write something that will be transpiled to a quantum computer.
And even if you took the path of having a more classical programming language that you could transpile to the quantum computer, you would need some different language paradigms in order for it to make sense on a quantum computer as well.
Okay, so like into the nuts and bolts. How do these things actually work, right? So you've got 50 qubits. You're writing logic operations that are addressing each individual bit. And then you turn the thing on, right? I mean, how does it actually work? What happens? I'm intrigued by this. I've never seen one, and it's super exciting.
At the moment, there aren't really any best form of platform for quantum computers, but there are a few different ways. One of them is called superconducting circuits, which is basically a normal computer chip that you supercool. Then it has some inductors and some capacitances, and a type of nonlinear inductor called a Josephson junction. And this Josephson junction is basically a superconducting wire with a hole in the middle. And then you would think, all right, now electrons can't pass through this hole.
Okay, yeah.
But a quantum mechanical effect is tunneling.
So sometimes they can.
Yeah, so in the quantum mechanical regime, they can tunnel through.
Yeah.
And then depending on where the electron is, that is the state of the qubit.
Oh, right.
Yeah.
And so you don't actually know until you observe it whether the electron is one side or the other. And that's
Exactly.
that's the different.
That's more or less the idea, yeah.
That's super cool. Is that the sort of thing you've been working with?
That is one of the computers that we're accessing. We're also using someone called trapped ions.
Oh, is this out of Duke? So there's some friends of mine who actually were working on this. Is in the US, is it? Or
Yeah, there is the IonQ in the US. Yeah. So they're trapping charged ions in magnetic fields. And then these ions are, because they're atoms, they're quantum mechanical. And they are built in a qubit because it's a two-level system. And then they can manipulate these ions and work them as quantum mechanical bits.
And you've then got the potential controversy around what Google are calling quantum computing?
Yeah, Google, they're using superconducting circuits.
Right, they are as well.
Yeah. So there are a lot of different platforms. Those were just two. There are at least 5 more on the top of my mind.
Right.
I think those two are the most common one. Those are the ones that you can access on cloud hardware providers such as AWS or Azure.
And we've got these multiple different types of quantum computing system, I guess. And then I hear a lot about, I read a lot about, or at least I see a lot of on phys.org, lots of questions about things like error rates and error correction, and how, hey, we've got this amazing ability to do this calculation, but the state is only coherent for like a fraction of a millisecond. So,
yeah.
And what challenges, I guess, are you facing at the moment with these systems?
Yeah. So right now they're very fragile. They're cohering or decohering very fast. So you can do a number of gates or operations on each qubits, and then they just start doing random stuff that you don't want them to do. So therefore you need error correction, sort of like you have in a normal computer. We just don't notice it anymore because it's so good.
Yeah.
But we need that at some point, and then we'll make perfect qubits that doesn't do random stuff. But that is also a couple of years down the line.
Should be mentioned that error correction is a more complicated subject on a quantum computer, because if you were to measure or read out the result of the computer in order to see whether or not a bit has been flipped, you destroy the state. So you need to be able to measure in kind of an aggregate way over several bits in order to see if a parity is obtained or some other feature of the sequence of bits, and then you can do some operation based on the result of that measurement. So that's also more complicated on a quantum computer. Everything is more complicated.
Well, which, I mean, everything is more complicated, I would say. It certainly sounds it. I mean, what's the why? I mean, it's really, it's super difficult science. Superconducting, hey, we're just going to super chill stuff down to like minus 250, like C or something, right? I mean, that's not easy to do. So the hardware is like super expensive. It's a difficult way to program. You have to learn a whole new approach to doing things. What's the benefit you think we're going to be able to, and be hyperbolic here, right? I mean, this is the time to be hyperbolic. So
so hopefully it's going to open up possibility to calculate, for example, new molecules that we cannot calculate on normal computers because they become too complex. So as I think Feynman said it when he proposed using quantum computers, that if you want to simulate something quantum mechanical, you better make a quantum mechanical simulator. And that is basically the idea of a quantum computer.
Yeah, also because they're likely going to be slower than normal computers for a long time. There's this famous case of factoring, where in principle you should be able to factor enormously large numbers much faster on a quantum computer. Yeah. That's of course very interesting from a maybe theoretical point of view, or if you're cracking codes, but also from a more I mean, if you want to build new stuff, then being able to calculate on more different types of materials more accurately, it doesn't necessarily have to be faster, but it can be more accurate, for example. So there's definitely a potential there.
Yeah, because I read a lot about quantum safe encryption or future, not perfect forward security is no such thing, right? Certainly when quantum computers get good enough at factoring, or fast enough, I guess, as you say. And is this going to be another real area where we're going to see lots of changes, you think, in the future, in terms of security, privacy, encryption, these kinds of things?
I think quantum computers are probably at some point going to break the RSA encryption because they can factorize large prime numbers. But luckily, quantum computers also have a built-in way of encryption. So it will just be that our encryption will have to change, but it has to do that all the time. Encryption is not something static.
Yeah, sure.
So at some point, quantum will just play a bigger role in encryption.
And it should be mentioned that even though RSA is vulnerable to quantum attacks, there are lots of other systems that are more resilient towards it. So there are classical ways around it. It's going to be important at some point, but it's not going to break the world in that way.
There's one that's on the tip of my tongue, but I can't remember it now. It'll come to me in a minute. Cool. That's super interesting. So in terms of so we've got a range of problems that can't classically be addressed by normal classical systems. We've got the hardware there to do it. It's obviously hugely expensive, hugely complicated, and only about 4 places in the world can afford to do it, right? But hey, you can access it over AWS, self-service, fantastic. And we're talking about things like chemistry and risk. So I guess the whole stuff in finance around pricing models. There's a lot of quants already in banks who are already using these kind of the similar sort of quantum equations to model risk and things internally. What about things like slightly chunked up a bit? So because biology is the classic example of modeling actual biological systems, so one level above the chemical. And that's super, super difficult, right? I mean, we only tend to be able to do that by observation almost. Is that another thing that is...
That is hopefully some of the things that the quantum computer will be able to do, which the classical computer cannot do at the moment.
Especially in pharmacological applications, sometimes you have a very small active site on an enzyme or a protein, where if you could increase the accuracy of that calculation, you would be able to much more accurately predict, for example, which kind of molecules could have some desired effects. So their quantum computer is envisioned to be useful at some point.
And are you seeing interest now from big pharma, from these organisations into the approaches that you're sort of championing?
Yes. Yeah, we're talking to several big companies, and also the EU are backing us.
Just a nice smile, and the EU, just saying that, that's awesome. That's super cool. So I guess there's a whole sort of ecosystem around this stuff as well, right? In terms of making the hardware things like cheaper. There's been a lot of research I've seen recently into breakthroughs into not room temperature superconduction, but being able to bring the temperature or new materials that are superconducting at higher temperatures. Is that sort of stuff all feeding in? Do you think there's going to be this sort of blossoming, like a sort of compound effect where you get lots of things coming together and suddenly we're going to see this quantum computing?
Well, yeah, there's a lot of small steps that needs to be taken, and room temperature superconducting circuits would be very nice. There will be a huge step on the way. But currently the biggest challenge is simply to make the qubits more stable against noise.
Okay, and so how many qubits are we talking about? Is it hundreds?
Around. I think the record right now is around 400.
Right.
Yeah,
that's super cool.
Yeah.
But they are not all connected, right?
No, they're not.
So you cannot do arbitrary things with them.
No, that's another problem. That when you do qubits, you have to lay them out in a grid, and they have to be close to each other before they can talk to each other. So that's a difficulty of making everyone talk to each other.
So it means it limits the number of which bits can you do which instructions on, basically.
Right. I see. Yes. Okay. Right.
I can't just swap 2 bits if they're far away from each other.
Right. What you need, it's one of these, it's like an Uber's type thing where what you need is actually a quantum computer to help you design a quantum computer, right?
That would be very
like
nice.
a 3D kind of grid of qubits or some kind of strange geometry that's going to allow you to kind of more easily program them.
Yeah.
But there's no reason to think that's not going to be an ingredient in the future. I mean, why not use the tool that you're developing to improve the tool? But it's unclear, right?
So what are you most excited about?
I think I'm most excited about the fact that I'm actually working with quantum computers. I mean, that's a childhood dream of mine. I saw it in science fiction movies, and I was like, that sounds really, really cool. And now I'm doing it.
And is it really, really cool?
It is really, really cool.
How about yourself, Soren?
Well, I mean, I also did a PhD within related areas, not quantum computer specifically, but since then I've been doing normal computer software engineering. But it's extremely nice to get back to an environment that's very research oriented and doing stuff with quantum mechanics that I know from my studies. And also, I really enjoy delivering high quality, robust software for customers that just works the way they expect it to. So I think bringing that, taking the prototypes that people do in quantum computing away from, or bringing them out of academia and into industry so that they're actually usable in a very friendly way, that really triggers me. I think that's super interesting. And then at the same time, being allowed to use thousands of computers at the same time to do a calculation. It's always fun.
It's always fun, yeah. I mean, that's actually a really interesting point. I mean, it hadn't really occurred to me. How do you test this stuff, for example? Because we were talking about industrialization or engineering.
That is a really good question. Right. Yes, because I've been thinking a lot about it because I care a lot about tests because I want to deliver robust software. Yeah. And it's not clear at all because as we can attest to, running stuff on a quantum computer right now is super expensive. Mm-hmm. So you're not going to put your quantum algorithm into a continuous integration test because that would just ruin you. Yeah. And you cannot run the test on an input that makes sense. As soon as you go over 40 qubits, you basically do not have enough memory. Maybe you can do 50. I don't know what the limit is, but then you run out of memory on planet Earth in order to simulate it. So maybe some kind of formal verification system could make sense, or maybe we just have to do extremely careful code review to begin with. I don't know, but it's unclear what the good solutions are. I don't know if there are any good solutions right now.
That's really interesting. Actually, anyone out there interested in testing quantum computing? There's obviously some kind of some opportunities. I mean, actually at Thoughtworks we've built an entire company more or less on the idea of like industrializing, making sort of new paradigms more robust and stable and kind of, so for example, like machine learning, that was a classic kind of Wild West, kind of full of, I won't say cowboys, that's way too strong, but lots of data scientists who are applying really interesting statistical models and writing really interesting algorithms and so on, building interesting models, but without some of the sort of the techniques you would expect from modern software engineering, things like continuous integration or delivery, or even versioning, or even being able to reuse the same model twice in your etc. etc. But there's been lots of advances in that recently. Things like continuous delivery for machine learning and feature stores and all these kind of cool things. So I guess there's lots of opportunities, or will be. Yeah.
And I think it's also an interesting question just for high performance computing, because a lot of the existing tools out there are either tools with a very isolated domain where you kind of can't test that domain, but if you're doing a larger calculation over a huge chemical system where nobody knows what the answer is, how do you test that? Because just running a single calculation might take a month or weeks, and you need to, of course, to have any degree of confidence, you need to test things in isolation, but the next step depends extremely sensitively on the step before. So there's also a lot of difficulties in delivering robust software for that kind of setup as well.
So I guess in things like meteorological kind of research, those sorts of things, where you're looking at cell-based kind of Monte Carlo-like algorithms. Those
for example, yes. Yeah. So that's also difficult to test, I find.
You mentioned Feynman, of course. Monte Carlo was adjacent to him, right? That was von Neumann in Los Alamos. You came up with that with Stanisław Ulam. So what was I going to say? So yeah, I mean, I'm intrigued by this idea now of sort of industrialization kind of process. And testing, and the idea of a formal methods. But I guess the downside generally with formal methods is they take a long time themselves, right? So Is that? But is it something that maybe is going to be worth it actually invest in that sort of thing?
It's a good question. I mean, we have some people working roughly in that area, but it's not really clear if it makes sense because if the quantum program is complicated enough, you of course cannot verify it formally. So there's definitely limits to what it can do. But if you can verify some of it, maybe you just need to do what can be done instead of doing what's perfect. So,
super interesting. Yeah. And so in terms of high performance compute, these are the sort of problems that you're working on already in the sort of chemistry spaces, these sorts of spaces, or is it?
Yeah, so right now, chemistry, pharma, and financial applications. So Monte Carlo and optimization and hardcore chemical calculation stuff like that.
Oh, super cool. Well, I think probably that's a good point to come to an end of this conversation. So thank you so much, Stig and Soren. I murdered your names again, and I'm terribly sorry about that. But thanks very much for joining us for this episode of GOTO Unscripted. I've been James Lewis, and see you another time. Bye-bye.